Okay, good morning, everyone. Let's get into our next problem, question 15. We are given the revenue function r of x equals 2646 x minus 0.18 x cubed for the domain 0 to x to 90. Okay. So find the local extrema for the revenue function, if there's a local maxima, local minima, if the graph is concave upward, or if the graph is concave downward. Okay, so first things first, let's graph this in our calculator, and then we're going to take our first derivative. So let's just do our first derivative real quick, okay? So r prime of x is 2646 minus, this is going to give us 0.18 times 3, which comes out to 0.54 x squared. Okay, and so we're looking for local extrema, so we can set this equal to 0. So 2646 minus 0.54 x squared equals 0. Let's solve for this. So 2646 equals 0.54 x squared. Divide by 0.54 x squared equals okay, this equals 4900. Then we're going to take the square root of both sides. So x equals 70. Okay, so now let's graph this. We're going to type in our function 26,460x minus 0.18x squared. We know this is our domain, so go to the window, change your x-min to 0, from 0 to 90, and then we don't really need a y minimum, but we need to figure out our y max. So let's go second graph, go to our table, scroll to 70, and see what our value is there. So it's 123,000. So I'm just going to go back to my window and change my y max to 150,000. That's going to give me enough space to view the entire graph. Okay, so now we're going to hit graph, and there's our function. We can see that it is concave down over this entire domain that we were given, right, to evaluate. And we can see that we have a maximum point. So let's confirm that. Second, trace. Gonna use number 4, left and right only. So we're gonna scroll over to or slightly to the left of the maximum. Press enter. Scroll over to the right. So we're slightly right of the maximum. Hit enter. Hit enter again. And this confirms our maximum occurs at x equals 70 and y equals 123,480. Okay, so let's go back to our responses over here. A, find the local extrema. The local maxima is at x equals 70. So that's part A. What is the local minimum? There is none, right? We did not have a local minimum in our function that we graphed. On which interval is the graph concave upward? It is not concave upward. We can see that. And then on what interval is the revenue function concave downward? Over this entire domain that we were given from 0 to 90, the function is concave downward. So there's our response from 0 to 90. Okay, let's move on to the next question. Excuse me. Okay, 16. Find the absolute minima, absolute maxima for this graph. So here we're going to make this graph as large as possible. Okay. And this is telling us over the interval from 0 to 10. So on these functions that are depicted here, make sure you're paying close attention to the intervals that they're asking you to evaluate over, okay? So here, look at my cursor on the screen. It's telling us over the interval 0 to 10. So on our graph, we have the interval 0 to 10. So they want us to evaluate over this entire domain. Okay, so the first part is asking for the absolute minimum. Where does this occur at? So we look for our minimum point here. We see, no, this is our minimum. Okay, within this entire domain, this is our lowest point, and that is going to occur at x equals 0, and our y value is 1, 2. So the absolute minimum is 2 at x equals 0. Okay, so now, again, if you wanted to sketch this really quick, so you have something in your notes, 1, 2, put your point there, graph this really quick, 0, 2, minimum, okay? Now it's asking you for the local, the absolute maximum. So it's this point over here, and that's at x is 10, and your y is 20, 19, 18. Okay, so that point right there, y equals 18. So here's going to be 10, 18 max. Okay, so that's a quick way you can show that in your test notes. And then your response over here, the absolute maximum is 18 at x equals 10. Okay, next question. 17. They are giving us the function f of x equals 2x to the 4th power minus 9. And find the absolute extrema. Okay, so let's graph this. 2x raised to the 4th power minus 9 graph. And I want to change my window to negative 90. I think 300 will be fine. Okay. Let's change our x's. Let's do negative 25. Okay, you can see it a little bit better. We still want to zoom in here. So let's change our y min to maybe negative 100. Okay, so there we can see our graph pretty good. We can see, right, that it has a parabolic shape and something is occurring here. We have a minimum, okay, and the graph is concave upward. Okay, so down here we know there is no maximum. There's no absolute maximum. Okay, here we want to find the absolute minimum. So we're going to do second trace. We're doing a minimum now. So number 3. We're going to scroll slightly over to the left of the minimum point, hit enter. Scroll slightly to the right of the minimum point, hit enter again. And this is basically 0. Okay. So at x equals 0, y equals negative 9. And again, so you can have something in your notes, you can sketch it really quick like this. 0, comma, -9. That's your minimum. Okay. And then you can also take the first derivative here. This is going to give you 8x cubed. Then you'll take 8x cubed, set it equal to 0, and then solve for x. So divide by 8 is x cubed equals 0. Then you take the cubed root of both sides, and x equals 0. So that's how we can still use our derivative properties to confirm this minimum point as well. Okay. And that's it for this problem. Let's keep going. Okay, 18. Okay, this one's where we really need to pay close attention to our graph and our domain. So let's see, our function is f of x equals x cubed minus 6x squared plus 9x plus 18. Okay, so for part A, we want to evaluate over the domain -3 to 6. So I'm going to graph this, and then I'm going to change my window specifically to this domain. Okay. So x cubed minus 6x squared, oops, minus 6x squared plus 9x plus 18. We're going to change our window to -3 to 6. So -3 to 6. Let's see what this looks like. Okay, so we have this small curvature, right? I'm going to change my y to, let's see. Yeah, that looks a little bit, that looks a little bit better. Okay, so now I'm going to, this kind of looks like a maximum, this kind of looks like a minimum. I'm going to see what I can figure out, but we're also looking for the absolute maximum. So actually, we don't even need to do that. This is going to be our minimum. This point is going to be our maximum. Okay, so let's do a quick sketch. This over here is 6. This is -3. Our graph was down here somewhere. It went up. It went kind of like this, and then it went here. Okay, so this is going to be our maximum point, and this is going to be our minimum point. And now we just are going to use our graph to help us identify those points. So we're going to use second graph. We're going to scroll up to 6 and -3. We're almost there. Okay, so here you can see when x is 6, y is 72. So this point is 6, comma 72. And then we're going to keep scrolling up to -3. And at -3, our y value is -90. Okay, so that's how you can do a quick note and show your minimum and maximum using your graph. Okay? So part A, the absolute maximum is 72 at x equals 6. The absolute minimum is negative 90 at x equals negative 3 over the domain from negative 3 to 6. Okay, so that's part A. We're good. Now let's move on to part B. They're going to change our domain. So now we're evaluating from negative 3 to 3. So we need to come back over to our graph, change our window. Our x max is 3. Graph again. And there we go. So now I'm going to change this y up here a little bit to maybe 65. Okay, and we can see, right, that this has more of this concave down behavior. So I'm going to sketch this really quick again. Over here is 3, over here is negative 3. We start somewhere down here on the bottom. And we're going up and it kind of comes down. Okay. So now let's see if we have a maximum. We're going to use our graph. So second trace, number 4. We're going to be slightly to the left over here, hit enter, scroll over, slightly to the right, hit enter again. And it's showing us that, in fact, we do have a maximum, and that's occurring at 0.99999. So that's basically 1, x equals 1, and y equals 22. So we do have a maximum point here. And that's 1, 22. Okay. And then this is still our absolute minimum at negative 3, negative 90. This point hasn't changed, right? We still know this from our previous domain. Okay, so now part B, the absolute maximum is at 22 at x equals 1, and the absolute minimum is negative 90 at x equals negative 3. Okay, so that's part B. Now let's do part C, which is over the domain from 2 to 6. So we're going to change our graph one more time. Let's change our window. We're going to change our x min to 2 and our x max to 6. Let's graph that. And I need to make my y back to 100. Okay, perfect. So let's do another quick sketch. Our y-axis, we're starting at 2, 3, 4, 5, and this is 6. Okay, and this is going like this. Okay, and we already know this value at 6 is a maximum point 6, 72 from part A. Okay, and then this clearly looks like our minimum is occurring somewhere in here. So let's use our calculator, okay? So second trace, we're looking for a minimum, 3. So let's slightly over here, right? We'll hit enter, and then again, until we see this function start increasing. Okay, so now slightly to the right, hit enter again. And there's our minimum. It occurs at 3,18. 3,18. This is your minimum. Okay. And so again, part C, the absolute maximum is 72 at x equals 6. The absolute minimum is at 18 at x equals 3. All right, that's problem 18. Question 19. Okay, it's giving you some information and it's asking you to determine if this is a local maximum or local minimum or local minimum. I need more coffee. Given these details. Okay, so basically they're telling you, okay, they're giving you all this definition information. So they're telling you 19, you have your first point, x equals 8, f evaluated at 8. So some point on your graph where x is 8, and then you evaluate your function at x equals 8. If f prime at 8 equals 0, this is telling you you have either a local min or local max. Okay, so that's the first thing we know. We have something reaching either local minimum or local maximum. Then they're giving us our f double prime definition evaluated at x equals 8, and that is less than 0. So this is also indicating to us now that this is in fact a local maximum. Okay, so it's just using your definitions. Make sure you have this in your notes, in your toolkit, so you're able to identify based off of your first derivative and your second derivative if this point in space is either local minimum, local maximum, or if it's doesn't represent anything. Okay. All right, question 20. See, a company manufactures and sells X cell phones per week. The weekly price, demand, and cost equations are given below. Okay, so we have price, cost. What price should the company charge for the phones, and how many phones should be produced to maximize the weekly revenue, and what is the maximum weekly revenue? Okay, so they gave us P, which is 500 minus 0.1x, and cost 20,000 plus 135x. So now we need our revenue function, which again we know is P times X. So P times X, it's going to give us 500X minus 0.1X squared. We want the maximum weekly revenue. So we're going to find the first derivative, which is going to give us 500 minus 0.2x. Then we're going to take this and set it equal to 0. We're going to finish solving for x. And that is going to give us x equals 2,500. And now evaluate your revenue function at 2,500. So R at 2,500 equals 500 times 2,500 minus 0.1 times 2,500 squared. And that's going to give you 625,000. Okay, this is our revenue at this production level. Okay, so now we also want to calculate the price at this production level. So P equals 500 minus 0.1 times 2,500, and that's going to give you 250. Okay, so that's for part A. The company should produce X quantity, 2,500 phones, each week at a price of 250. The maximum weekly revenue at this quantity is $625,000. Okay, so now part B. What price should the company charge for the phones, and how many phones should be produced to maximize the weekly profit? And what is the weekly profit? Okay, so before we're maximizing the revenue, now they're asking us to look at this differently and maximize the profit. Okay, so we need to go ahead and take our profit, big P, right, equals revenue minus cost. So we're going to figure out our revenue function first. Or I'm sorry, our profit function first. So revenue was 500 x minus 0.1x squared minus our cost function, which was 20,000 plus 135x. Simplify this. So our profit equals negative 0.1x squared plus 365x plus minus 20,000. Yeah, this negative distributes. So minus 20,000 minus 135x. Okay, so again, I want to maximize this profit function. So I'm going to take the first derivative. And that's going to give me negative 0.2x plus 365. And now I'm going to set this equal to 0. 0.2x plus 365 equals 0. 0.2x equals 365. Divide by 0.2. X equals 1825. Okay, so now I'm going to plug in this X into my profit function. One 1825 squared plus 365 times 1825. Okay, and that's going to give me profit evaluated at 1825 equals 313,062.5. And then price equals 500 minus 0.1 evaluated at X equals 1825. That's going to give me a price of $317.50. That's kind of looks messy. $317.50. Okay. So part B, the company, in order to maximize the weekly profit, the company should produce 1825 phones each week at a price of $317.50 to generate a maximized profit of $313,062.50. Okay, so that's question 20. All right. Problem 21. A company manufactures and sells X television sets per month. The monthly cost and price demand function are below. Okay. Okay. Let's see. Your cost function is 75,000 plus 80x. And your price is 300 minus x over 30. Okay. To find the maximum revenue. So we're going to take revenue equals P times X. We have our P. So that's going to give us a revenue function of 300x minus x squared over 30. We are maximizing it, so we already know we need to take the first derivative of our revenue function. That's going to give us 300 minus 2x over 30. We're going to simplify our fractions. So that's 300 minus x over 15. Now we're going to take this and set it equal to 0. And then we're going to finish solving. So that's 300 equals x over 15 multiplied by 15 multiplied by 15. So x equals 4,500. Okay, that's for part A. This is our quantity, so we need to evaluate revenue at 4,500 equals 300 times 4,500 minus 4,500 squared over 30. The revenue at 4,500 equals $675,000. Okay, so that's for part A. Now part B, the maximum profit. We need to, again, find our profit function. So revenue minus cost. That's going to be 300x minus x squared over 30 minus the cost function, 75,000 plus 80x, and that's going to give you a profit function equal to negative x squared over 30 plus 220x minus 75,000. Then we are going to take our first derivative of our profit function, and that's going to give us negative 2x over 30 plus 220. Now we're going to set this equal to 0. And solve. Okay. And that's going to give us 30. And x equals 3,300. Now take this quantity and plug it back into your profit function. So profit equals negative 3,300 squared over 30 plus 220 times 3,300 minus 75,000. And that's going to give you a profit of $288,000. And then we need to find our price. And that's going to be 300 minus 33 over 30. And that's going to come out to $190. Okay. Okay, so that's for part B. The maximum profit is $288,000 when 3,300 sets are manufactured and sold for $190 each. Okay. So now they want us to, in part C, evaluate if we have a $6 tax added. So we're going to take what we have for our profit function here. Right, this is what we had from part B is our profit function. Plus 220x minus 75,000. That's our profit function. Now we're going to be taxed $6. So minus $6 per unit. So minus 6x. And our new profit function is negative x squared over 30 plus 214x minus 75,000. And we're going to do the same thing as with part B. We're going to take the first derivative of our profit function, and that's going to give us negative 2x over 30 plus 214 we can reduce this to negative x over 15 plus 214. Now we're going to set this equal to 0. And solve. So that's going to give us x over 15 equals 214. X equals 3210. And then I plug 3210 into my profit function, and I also plug it into my price function. Let's see, 300 minus 3210 over 30. Price is going to equal $193. And profit is going to equal 268,470. Okay, so the profit at this evaluated at this X amount of units is going to generate this much profit, $268,470, and our unit price is $193 at this quantity of X. Okay, and that's part C. Keep going. What is this? 22. Okay. So a car rental agency rents 480 cars per day at a rate of $20 per day. For each $1 increase in rate, 10 fewer cars are rented. At what rate should the cars be rented to produce the maximum income? And then what is the maximum income? So we are going to let's start with the car rental price. That is going to be represented by $20 per day and a dollar increase. If 10 fewer cars are rented. Okay, so for every dollar increase, 10 fewer cars are rented. Okay, so now we have number of cars rented. That is 480 minus 10x. For this price increase, you reduce your quantity in cars rented. Okay, so that's how we are going to account for that. Now, our income is a function of these two factors. So 20 plus 1x times 480 minus 10x. Okay, now distribute your factors. I'm just going to make life easy for us because that's how we're just going to do it. So I equals 9,600 plus 280x minus 10x squared. Okay, so now I'm trying to maximize my income. So now I'm going to take the first derivative. So I prime is going to give me 280 minus 20x. So I'm going to set this equal to 0. So 280 equals 20x, divide by 20. X equals 14. Now plug in x equals 14 in your income function, and that is going to give you $11,560. Okay. So really it's just setting up these two factors, doing some algebra, and then take your first derivative and solve. Okay. Question 23. A fence is to be built to enclose a rectangular area of 1800 square feet. Okay, so you have a rectangle, X times Y, and they're already telling you X times Y, your area is 1800 square feet. Okay. The fence is along 3 sides is to be made of a material that costs $3 per foot. So 3, 3, 3. The material for the 4th side is $9 a foot. Doesn't really matter how we do that. Okay. Wait, no. Is that how I do mine? Okay, this is gonna be 3x, 3x. This is 3 on your y side and 3 on, I'm sorry, 9 on your other y side. Okay. 3x, 3y, 3x, 9y to account for the side that costs $9 per foot. Okay. Find the dimension of the rectangle that will allow for the most economical fence to be built. So minimize your cost is essentially what it's telling you. Okay. So let's add our sides for the cost. So our cost is 3x plus 3x plus 3y plus 9y. Combine our like terms gives us 6x plus 12y. Okay, now I'm going to come back up here and I need to make this into a function of just one variable. So I'm going to solve this for y, and y is going to equal 1800 over x. So I'm going to substitute this in here for my y variable. So c equals 6x plus 12 times 1800 over x. 6x equals 6x plus 21,600 over x. Now I want to minimize this cost, so I'm going to take the first derivative. And it's going to give me 6 minus 21,600 x squared. Now I need to solve, take this, set it equal to 0. So 6 minus 21,600 equals 0. So 6 equals 21,600 over x squared. This is going to be 21,600 divided by 6 to get our x squared isolated. Then we're going to take the square root of both sides, and x will equal 60. So your short side, okay, so now let's go back and finish solving this y. So y equals 1800 divided by 60, which gives us 30. Okay, so for your problem, the short side is 30 and the long side is 60 feet. Okay, and that's it for this problem. All right, 24. These are a little bit longer. Okay. A manufacturer of hospital supplies has a uniform annual demand for 320,000 boxes of bandages. So 320,000 is your demand. Just writing some notes. Okay. It costs $10 to store one box of bandages for 1 year and $250 to set up the plant for production. How many times a year should the company produce boxes of bandages in order to minimize the total storage and setup cost? Okay. Excuse me. So the first thing we're going to do is set up our storage cost. And that's going to be the $10 to store box times your average quantity per year. And that's going to equal 5x. Okay. And then we are going to set up our number of production runs. That's going to be 3,200. I'm sorry, 320,000 divided by X, the quantity per run. Okay. So now our setup cost is the cost per run, which is $250, times the number of runs, which we already set up, over X. Okay. So this gives us a large number, 80 million over X. Okay. So now we take our storage cost, let's put a star there, and our setup cost, and combine those to create our cost function. So our cost function is storage cost, 5x, plus our setup, our run setup cost. Okay, now we know that. Now we want to find, we are what? Minimizing our cost. So we're taking x cost prime. So first derivative of this function is going to give you 5 minus 80 million over x squared. Now we want to set this equal to 0 and solve for x to minimize this. So 5 minus 80 million over x squared equals 0. We want to isolate x squared, so that ends up looking like x squared equals 80 million. I keep wanting to say 1,000. Divided by 5, so x squared equals 16 million, and then take the square root of both sides. X equals 4,000. Plug 4,000 back into your cost function. And then also into your run. Okay, so 320 divided by 4,000 gives us 80. And then, oh, I guess we really don't need the cost, huh? All right, we just need all the work to get to the quantity X. And then once you have this, take that value and bring it back into your number of runs that you're going to utilize in order to generate this demand. So 320,000 divided by 4,000 is going to give you 80 runs. Okay, and that's actually pretty not bad. That's the problem in general. It's just this part, setting up your storage cost, your run average, and then your setup cost using your run average. Then you set up your cost function, which is storage cost plus setup cost. Okay, first derivative, solve for X, take your X and plug it back into your number of runs equation, and that's going to tell you how many runs you need in order to minimize your cost for producing and meeting your demand. Okay. Let's see. Number 25 is basically the same. Okay. So your demand is 700 mice. Your okay, so first let's start with our feeding cost. That is it costs $8 to feed a mouse for 1 year. So average quantity, so $8 is what it costs to feed a mouse times the average quantity. Okay, so that's going to reduce to 4x. Now, your number of runs is 700, your demand over x. And then your order processing cost is let's see, it was $28 times your demand divided by quantity per run, your number of runs. Okay, so the price to process an order times the number of runs. Okay, so again, your cost function is your feeding cost plus your order processing cost. And this is going to equal 19,600 over x. Okay. So your cost is going to be 4x plus 19,600 over x. Okay. And again, we want to minimize our cost. So we need to find the first derivative of our cost function, which is going to give us 4 minus 19,600 over x squared. We're going to set this equal to 0 and isolate x squared. So that's going to end up looking like x squared equals 19,600 over 4. And then we're going to take the square root of both sides. And then x equals 70. Okay. And this is our x quantity. So again, in order, we need to minimize our runs. So we're going to plug that in. 700 divided by 70 gives us 10 runs, okay, to minimize our cost. But let's look at what this question is asking us. So question 25 is asking us how many mice should be ordered each time to maximize. So that's your X, your quantity. So 70 mice should be ordered to minimize your number of runs, which would produce only 10 runs, and that would generate the minimized cost here. Not asking us for the minimized cost. This problem is not asking us for how many runs. It's asking us how many quantity we should be ordering. Okay. Now let's go back to 24, because I think that's another distinguishing point. In 24, we were being asked, okay, our quantity was 4,000, but 25 is, I'm sorry, question 24 is asking us the company should produce boxes of bandages how many times a year. So that's basically asking you how many runs a year. Okay, so 24, that's what's different. 24 is asking you how many runs. Question 25 is asking you how many units per run. Okay, so just make sure you're paying attention to the details in those two questions and specifically the information that they're asking you for. Okay, all right, guys, I hope this video helped. Again, if you have any questions, just feel free to send me an email, and good luck on your next test.